Okay, so thank you very much, Neil, and thanks to Neil, Boris, and the organizers of this meeting for inviting me to speak here. Also, as I was realizing the opportunity to remind myself of what real winters are like after spending close to a decade in warmer climates. But but on the positive side, I got a terrific view of the Alps while flying in. So, any case, so the topic of these lectures is on higher spin theories and their relation to holography. So higher spin theories are themselves a vast topic which have been developed for 2 decades, it's actually more than 2 decades, for 3 to 4 decades, and I will not be able to do justice to that. I mean, that would require separate lectures in themselves. What I will rather do is to tell you enough, a little bit, about higher spin theories so as to tell you its significance in the context of holography and why it's a very interesting arena to explore issues in AdS CFT. So in fact, the contents will be as follows. I'll start with a few motivations, at least 3 motivations which I personally have in studying this topic. And then I'll tell you a little bit about these higher spin theories. As I said, it will be fairly somewhat schematic. It's a very technical topic, and even I can't claim to understand all the intricacies of the Vaselia construction of these theories very well. But I'll try to tell you kind of a roadmap, give you a sort of a roadmap into these theories, and then so this will sort of cover. So the 2 lectures today will be more or less this, and if I have some time, I'll get to the 3rd point, which is the application of these higher spin theories in the context of AdS4 to dualities to vector model theories in 3 dimensions, and then in the next 2 lectures we'll talk about a simpler class of these dualities for vector-like models now for the higher spin theories on AdS3, which, as we'll see, is significantly simpler than the more general higher spin theory itself, which is why I feel it's a good place to start learning about these higher spin theories and develop an intuition for them. So I will spend the latter 2 lectures mostly on these and the various checks, generalizations of these dualities. And finally, I will also mention something about some very interesting works that people have been doing about new kinds of black hole solutions in these theories, especially in the AdS3 case. So what are the motivations? So one motivation which to me is very important is that this can provide a handle on understanding classical string theory on very strongly curved AdS backgrounds. I'll elaborate a little bit on this shortly. So a general question independent of these higher spin theories is how to understand classical string theory on AdS backgrounds whose curvature is of the order of the string scale. In particular, that's the regime where the theories that we understand best are in the AdS CFT are where the duality is to a perturbative gauge theory when the AdS is of order string scale. So that's an important question, I think, to understand. And I'll try to tell you why higher spin theories have something to say about that. And then I'll talk about these examples As I mentioned, these examples of AdS CFT and AdS4 CFT3 and AdS3 CFT2, these are in some sense simpler and in fact non-supersymmetric examples of AdS CFT, and they are theories which are different from the usual gauge-string dualities where you have a full-fledged gauge theory, because these are vector-like large N theories. So the field theory is simpler and potentially the dual is simpler. You can hope to understand many aspects of the holographic connection and so on. So this is an important example, an important class to study well. Also, I should stress the non-supersymmetric aspect of it, since most of our examples have been the well-studied examples are typically supersymmetric or sort of close to supersymmetric examples. So we would like to have some genuinely non-supersymmetric cases as well, and see whether there are qualitatively new properties and so on. Finally, distractibility might help us learn something about the stringy nature of geometry. For instance, we know that string theory resolves many singularities. It provides some kind of microscopic description for black hole entropy, etc. But this is typically done in a way which is an expansion around the Einstein theory, and maybe with higher derivative corrections, but you expect that in a full-fledged string theory, certainly in the cases of these AdS CFT where the radius is of order string scale, the geometry is intrinsically stringy, and there's a much larger gauge invariance in string theory, and how do we then talk about notions of black holes, which are very much tied to a space-time picture when you have an intrinsically stringy geometry. So this is another example. This is another kind of a question which maybe we can learn something about, and towards the end of the talk, towards the end of these lectures, as we'll see, we'll try to say more about what we've learned about that in the context of AdS3 at least. So as I said, we'll focus on the second and third questions, we'll focus on the second and third question, not because the first one is not interesting enough, but I think very little progress has been made on that. But in the rest of the introduction, I'll tell you what we know about the first question, and after that we will sort of leave that aside. But I think that's a very important arena where we can potentially make progress. So please stop me whenever you have questions, etc. So we know that theories of gravity on AdS are dual to conformal field theories on the boundary. This is believed to be a more general fact than just the examples that we've understood better. In particular, there is a classical description in which the Newton's constant or the string coupling goes to 0, which is described by the large n, or the n goes to infinity limit of CFT. So you need large number of degrees of freedom in the CFT, and n is related in some inverse way to the Newton's constant. So the conventional Einstein theories, which are of course classical theories of gravity, arise in a double limit, namely when you have not just a large n theory, but also the coupling in that theory goes to infinity. So it's a double, it's an n goes to infinity and a lambda goes to infinity limit. And most of the calculations in AdS CFT are in this regime, which corresponds to sort of an ultra-strong coupling in the CFT. But very often one is interested in conformal field theories in which the coupling is of order 1. I mean, it's strongly coupled, but not infinitely strongly coupled. So that's where you often lack that you lack any techniques to study, for instance, in these popular examples of condensed matter physics, you wouldn't expect the coupling to be, in some sense, infinitely large, but something of order 1. In any case, in the examples that we've studied, if we try to understand the CFT with the coupling of order 1, then we need to quantize the string theory on AdS, meaning we need to understand the correlation functions, the spectrum of the string theory on AdS, in which the radius in string units is proportional to lambda to the 1/4 in the case of AdS 5, for instance. CFT4, and if this is of order 1, that means the string theory is of the string theory is on a or on an AdS with order 1 in string units radius, and this is even for the maximally supersymmetric string theory on AdS 5 times S5. We don't have this degree of analytic control. That we can quantize it and read off the full spectrum. Though people have been trying, in particular in the pure spinor approach of Berkowitz and so on, but it's still not been developed to an extent where we understand the answer. So in some sense, we need to look for a different expansion point other than lambda goes to infinity, which was the Einstein limit. So typically whenever you have something, a regime which is difficult to reach through taking, say, lambda goes to infinity limit, you try to go in the opposite direction. So you might try to start from lambda equal to 0, which is a free field theory from the point of view of the dual CFT, and this might be a good idea because, as we'll see, at this point, there's a much larger set of global symmetries in the theory than at a generic interacting than in a generic interacting theory. So in some sense, of course, we know the free field theory is special, but there's a precise way to say how special it is. One way to characterize it is that it has an infinite number of conserved currents of arbitrary spin. And here's an expression for some of these currents in a theory, let's say, with some adjoint scalars. Just for definiteness, I've chosen phi to be an adjoint scalar and written down a class of conserved currents. So firstly, they are currents with S indices, and they come from taking various derivatives of, it's bilinear in the phi, in this particular case phi and phi dagger, with some number of derivatives acting on phi and phi dagger, and completely symmetrized in these indices. So this bracket denotes the symmetrization. And there are some combinatorial coefficients here, which at the moment are not so important. So you consider this this quantity, and it's useful to subtract out the trace pieces of this so that this is a traceless current. So these are So I've written for you a class of operators whose conformal dimension in the free theory is just s plus 2, because there are s derivatives, and there's in 4 dimensions it's s plus 2 because the scalar field has canonical dimension 1. And there are s derivatives. So all the terms here have scaling dimension of s plus 2, and these are what are called the twist 2 currents, because essentially delta minus s is what is called the twist, and that's equal to 2. In 3 dimensions, the scalar field has a canonical dimension half, so the corresponding delta is s plus 1, and etc. So this is a class of, I've just written for you some operators, and these are some combinatorial coefficients. These coefficients, by the way, are chosen so that this object transforms as a primary under the special conformal transformations. So, of course, under the dilatations, we see that it has a definite scaling dimension, but you can also demand that it transforms as a tensor of rank S should under special conformal transformations, and as a primary under special conformal transformations, and that uniquely fixes these coefficients. One can write them down in any dimension for any spin explicitly, but it won't be important for us. So finally, I claim these are conserved, and that's easy to see. So basically, if you take the divergence of this equation, basically you contract this del mu with one of these indices, and since we are in a free theory, del square phi is equal to 0, and so when you do this contraction, you will all the terms will be proportional to either del square phi or del square phi dagger, and therefore this is a trivially conserved quantity in the case of free massless theory. So these are certainly conserved currents, and I should say that in the case of s equal to 1, this is your usual charge current. S equal to 2, it's the stress tensor of this free theory, and but s equal to 3 and higher may be less familiar to people, but you can write these down, and as I said, they are conserved. So we are looking at a free theory, and we are interested in what the bulk dual is of this free theory. And the presence of these global symmetries associated to these conserved currents implies that in the bulk, by the usual AdS CFT correspondence, the conserved currents couple to gauge fields in the bulk, and in this particular case, you should have gauge fields in the bulk, which are also rank S symmetric tensors, which have this kind of, at least at the linearized level, they have this kind of gauge transformation. This is again for s equal to 1, it's the usual Maxwell gauge invariance. For s equal to 2, it's the linearized diffeomorphism. But for s equal to 3 and higher, these are more exotic gauge invariances. So whatever the bulk dual, whatever the bulk dual be for this free CFT, it should have in its spectrum these kinds of gauge fields, which have this larger gauge invariance than diffeomorphism. So in some sense, we need a generalization of Einstein's theory, which has all these additional gauge invariances, at least at the linearized level, it's these gauge invariances. And so in particular, you have these massless gauge fields of all spin. And when I say spin, I will always mean from now symmetric tensors of rank S, which go from 2 to infinity. Well, in this particular case, going from 1 to infinity, but you could consider, say, charge neutral fields, in which case you would have, you could have, for instance, even spins only, and so on. But typically an infinite tower of these gauge fields, and from the string point of view, so so what we are saying is that the string theory on AdS5 times S5 dual to this free theory has in its spectrum all these gauge fields, and they are believed to lie on the leading Rajesh trajectory of the string spectrum on AdS. By the leading Rajesh trajectory, one means so you know that string theory has an infinite number of Rajesh trajectories, but there is a particular Rajesh trajectory which has as its lowest state the graviton, which is present in any closed string theory. So all these states are believed to be lie on the leading Rajesh trajectory of the dual string spectrum. So in flat space, the analogous states would be the ones which are constructed by just some alphas acting on these kind of states with the alpha minus 1 oscillators excited, and that's what is called the leading Rajesh trajectory in the flat space string spectrum. We don't have the analog of this on AdS because, as I said, we haven't still quantized the string theory on AdS. But presumably when we do quantize it, we should find the leading Rajesh trajectory to consist of all these spin S gauge fields. So in some sense, it's a prediction for the tensionless limit of the string theory on AdS. Tensionless because, as I said, this is the relation in the case of the AdS5 string theory, and when this goes to 0, you're essentially saying that the string tension is because 1 over Ls is proportional to the string tension. Another way to say it is that the string tension is going to 0. So you have a set of infinitely many massless particles in this tensionless limit. So this was pointed out by these people about 10 years ago. So that's certainly that's interesting that the free theory has all these conserved currents and the dual theory has all these massless particles. But in the Yang-Mills theory, there are many more states than just these operators which have twist 2, because these were just the operators which had phi and phi dagger. But you can imagine operators with, so to say, higher twist, something like trace phi to the k, and with derivatives acting on them these would be instances of twist k operators. So there are gauge invariant operators in the Yang-Mills theories, and therefore states in the dual AdS corresponding to these other operators as well. And in fact, the full string theory would have a Hagedorn spectrum, an exponentially growing degeneracy of states, as opposed to that of a single Rajesh trajectory in which you have just one state at delta equal to 10, there is essentially one field, whereas in the full string theory you would have something of the order of e to the delta states. So clearly this is a small sector of the theory, of the full Yang-Mills theory. So you might think, what's so great about this sector? I mean, it's just some very special set of states. Of course, they are massless and so on. But one nice thing is that this sector of the twist 2 operators are closed amongst themselves under the OPE. So from the point of view of the field theory, in the free limit, if you take two of them and just consider O1 and O2, where the O1 and O2 are two of these operators, if you do a Wick contraction, you see that you will only generate another state, a single particle state that you generate, a single trace operator is only going to be one which has bilinears, because you will just contract one phi with one phi dagger, and you'll be left with another twist 2 operator. So this sector, at least in the free theory, is closed. And that's the sense in which you might think that there should be a closed subsector of the dynamics of the full theory, which consists of just these, so in the field theory point of view, this is closed under the OPE. This should be reflected in the bulk point of view, that these gauge fields sort of form a consistent closed subsector. So it's reasonable to expect that these dual higher spin gauge fields, which are massless, form a closed subsector. It's somewhat like a consistent truncation, which you have to supergravity in the opposite limit. So in the opposite limit, namely when lambda is very large, we know that we don't need to consider the full string theory. We can look at just the supergravity states. There's a consistent truncation to, say, the supergravity states on AdS5. And this is somewhat like that in spirit. So the question is, what is this consistent truncation? What is the dynamics of these massless higher spin gauge fields which describe this closed subsector? So you might expect that this is simpler than the full string field theory of this highly curved AdS, because after all, this is only one Rajesh trajectory. You don't need to consider the whole Hagedorn spectrum of states, which would be presumably described by closed string field theory on this zero radius AdS. So in fact, this dynamics is very strongly constrained by the presence of these higher spin gauge symmetries. So it's not only simpler from sort of just the point of view that there are fewer degrees of freedom, but it's also simpler in the sense that because of the presence of the higher spin gauge symmetries, these generalized diffeomorphisms that I wrote down a few slides ago, the dynamics gets very highly constrained. Just like the Einstein action is the only two derivative action consistent with diffeomorphism. These theories with these higher spin fields also have a strongly consistent, are highly constrained. And there's in fact, independent of all these string theory motivations, Vaselia, starting with work with Fradkin, and then later mostly by himself, but with also collaborators, constructed an almost unique theory, at least a classical theory, of these interacting higher spin gauge fields, and in fact, in AdS, first he constructed it in AdS D equal to 3 and 4, and then generalized it to more general dimensions. But the best known constructions, the best understood constructions are in D equal to 3, 4, and 5. So I'll always use the notation capital D for the dimension of AdS and little d for the dimension of the field theory. So this theory, even though it's very complicated, and I'll give you a glimpse of that shortly, it's of intermediate complexity between supergravity and full-fledged string theory. So it has many more fields than supergravity, infinitely many fields, but a smaller infinity compared to full-fledged string theory. And this higher spin symmetry, as I've mentioned, is a vast extension of the diffeomorphism invariance, and it's presumably part of the enhanced symmetries of string theory, which we believe actually even in flat space exist, and which people have at various points talked about but haven't really exploited. But I think this is a context in which you can study them quite explicitly. So that's the the consistent truncation is presumably this classical theory constructed by Vaselia, because, as I said, it's essentially unique up to a few parameters in particular cases. So this is presumably what this subsector of the string theory will also have, since, as I said, it's closed and has this higher spin symmetry. Yeah.
How do we know that it's unique?
Well, there's no proof in some sense, but I think the construction of Vasiliev is so tightly constrained that at least within that formalism, it's very, I think it's, you can show within that formalism, this is essentially unique up to certain things which I'll describe later. Yeah. So any other questions? Okay, so what about this higher? So this is well and good. I mean, you have these higher spin symmetries describing this sector. But what would be really interesting is if the full string theory was somehow organized according to this symmetry. So, of course, this symmetry determines the dynamics of this sector, but what about all these other Hagedorn, other Rajesh trajectories? Are they somehow organized by this higher spin symmetry? There's some evidence of this by, notably, from the group of Bianchi et al. But I think this is something that has been that has not been studied enough, and I think it would be really exciting if one could say that this symmetry somehow governs the full spectrum. And the other interesting thing would be if one can really show that this symmetry has a role to play even when you go away from lambda equal to 0. So at first sight, that might seem to be a little bit of a strong thing to ask for, a bit too much to expect, because in some ways it's very difficult to have higher spin symmetry in an interacting conformal field theory in greater than 2 dimensions. And in fact, recently there was this work by Maldacena and Zhebodev who showed an analog of a Coleman-Mandular theorem. Basically, what they showed is that if we have higher spin currents of spin S greater than 2, then the correlation functions of these higher spin currents will be that of a free theory, namely that of either free bosons or free fermions. So of course, like many other such theorems, indeed the Coleman-Mandular theorem itself, there are a number of assumptions. Firstly, it's true when you have finite number of degrees of freedom, and it can break down, and in some we'll see that it does get violated at infinite n, but for any finite n, this is true. And notice that they are not claiming that the theory itself is free. They haven't shown that. All they have shown is that the correlation functions of these operators in the theory are those of a free theory. It could well be that the correlation functions of other operators are not those of a free theory. But in any case, that might seem to sort of be dampening this hope of using this symmetry to study, to go beyond lambda equal to 0. But in some ways, I think it's not that's giving up a little too easily, because actually there are indications that this higher spin symmetry in the bulk is realized in some kind of a Higgs phase, namely that the symmetry is spontaneously broken. It's a gauge symmetry which is Higgsed by turning on the operators or turning on the fields corresponding to the coupling, which would be something like a dilaton. And when we know from from all your studies of the electroweak theory and so on, that even if if a gauge symmetry is Higgs, you still have a lot of the power of the gauge invariance. For instance, the Ward identities would still hold, so it may well be that this higher spin symmetry may be broken in a controlled way. And in fact, in this MZ paper, they do sort of show that correlation functions of these currents get sort of small corrections in a 1 over n expansion when you go away from a free theory, and I'll say a little bit more about that later. But so it might nevertheless be. So I think it's important to understand this kind of Higgs mechanism and what it means for the and try to connect that with this this work and how exactly the correlation functions may be constrained even without having it in a manifest form. In any case, all that I said was true for d greater than 2, like in the Coleman-Mandular theorem itself. The Coleman-Mandular theorem tells you that for d greater than 2, you do not have interacting theories with higher spin currents. But in the massive case, we know that in 2 dimensions, there are integrable theories which have an infinite number of conserved currents which have a higher and higher spin, and this is also true, and we'll see it's true for conformal field theories as well. So there's a large class of interacting theories in d equal to 2, which will in which you can go away from the free theory and still have the higher spin symmetry. So that's one reason to study the d equal to 2 case, because you can learn about how these theories are realized, how these symmetries are realized in an interacting theory a little better. So now I'll try to tell you a little bit about this Vasiliev theory, but before that, are there any questions? So this was my sort of general motivation about the relevance of higher spin symmetries to studying string theory on highly curved backgrounds, but from now onwards I'll not mention that aspect at all, but so if you have any questions regarding that. Okay, so let's let me try to tell you a little bit about this formidable Vasiliev theory. So it's, as I said, these higher spin symmetries are a vast generalization of diffeomorphism invariant theory, and this Vasiliev theory realizes these in a fully nonlinear fashion, just like diffeomorphisms are realized in a nonlinear way in the Einstein theory. And that was the main challenge in constructing the Vasiliev theory, to get a so-called non-abelian generalization of these linearized higher spin theories. And typically, these contain an infinite tower of higher spin fields, excepting for special cases which we'll consider in 3 dimensions. But typically, there's an infinite tower. These could be all spins going from 1 to infinity, or they could be all even spins from 2, 4, 6, so on. But you would typically have an infinite number of them. And they are, in some ways, the opposite of the Einstein theory. They do not in any sense reduce to Einstein's theory, because anyway you have infinite number of other massless fields. And the construction appears to contain an infinite number of derivatives, so it's non-local, and that's one of the peculiar features of these theories. Of course, you don't see it in a manifest way, but you can infer the existence of terms with an infinite number of derivatives. So it's but the precise nature of this non-locality has not been completely explored, and I think that's also an important thing to understand better. Another feature is that these theories have been written at the classical level, but even there, only at the level of equations of motion, which are complicated enough, as we'll see. And there's no action principle, which is known as of now, again, except in special cases in 3 dimensions. But there's no reason to, there's every reason to believe that there is an action principle. It's just that it hasn't been written down. The other feature is that the flat space limit of these theories are singular, namely if you take the cosmological constant to 0, or many of these terms, they just blow up. So the higher derivative terms are in fact suppressed by inverse powers of the cosmological constant. So the flat space limit does not appear to be very smooth, and this is at least pseudo-consistent with certain no-go theorems about the existence of higher spin symmetries in flat space, but there may be loopholes on both sides. In any case, I should just alert you that even though we'll be talking about the theory on AdS spaces, they can be equally well defined on de Sitter spaces, and there has been some initial work on this in the case of DS4, and I'll probably mention it in passing later. But these are some very general features of the Vaselia theory. So now let's sort of try to get our feet wet a little bit in these theories. So we'll start with the free theory. I mean, that's always a good place to start. So let's start with non-interacting theory of these higher spin fields in a curved background. So I'm sorry, is this visible? I shouldn't have maybe used this color. Yeah, I should try to avoid this color from. Well, it may. Okay. So the free theory is defined in terms of these fields phi symmetric tensors with S indices, but actually obeying an additional constraint, which is that they are sort of double traceless. So if you contract 2 pairs of indices, they must you set that equal to 0, and of course the linearized gauge transformation, which is the generalization of diffeomorphism. So for the free theory, we have just a linear gauge symmetry. So this condition, this double traceless condition, of course, operates only for spin 4 and higher, so that's why you've never seen it in gravity or anything like that. And maybe I can say a little bit more in one of the tutorials, but basically this constraint is necessary to ensure, I mean, it's nothing very deep, it's just to ensure that your field has the right number of propagating degrees of freedom of a spin S massless particle. So for instance, in 4 dimensions, we know that a massless particle is classified, the irreducible representations are classified by just helicity plus S and minus S states. So you want 2 physical degrees of freedom for every massless particle of spin S. This is automatic for the Maxwell field and for the Einstein field once you impose this gauge invariance, but it's not for for these fields, because if you look at the symmetric tensor of rank S, that has a very large number of fields, and the number of degrees of freedom is very large, so you have to sort of cut some down to write down a Lorentz invariant, a Lorentz invariant theory which describes just the spin S fields and not other helicity, lower helicity fields. So that's just a kinematic kind of a constraint, and that leads to the consistency with that requires actually that this gauge parameter is traceless. Just single contraction vanishes. So that's not difficult to see that consistency with this demands the single tracelessness of the gauge parameter. So the linearized equations, which were written down by Fronsdal probably in the late 70s, which are consistent with this gauge invariance, can be written as follows. This is the spin S Laplacian. So this could be in any curved background, so need not be flat space. Could be flat space, it could be AdS, any space. So this is the covariant derivative, the Laplacian from the covariant derivative, appropriate to the spin S field, and then times some pieces which involve some combinations of two derivatives. This involves a contraction, this involves sort of a single trace of field phi. And then if we are in AdS, if we are in flat space, these would be ordinary derivatives, and this term would be absent because it's proportional to 1 over the radius of AdS. But if you are in AdS space, there's, if you wish, an effective mass term, which is probably familiar to those of you who have studied, say, the gravitational, if you linearize Einstein action about AdS background, you get a particular value of these constants. So these are again some numbers which depend on the spin and the dimension. So this is some wave operator, second order wave operator acting on the field phi set equal to 0. And in the particular cases of S equal to 1 and 2, S equal to 1, it's exactly the Maxwell wave operator. S equal to 2, it's the linearized Einstein equation, either about AdS if you keep that term, or about flat space if you drop covariant derivatives in this term. So for S equal to 1 and 2, they are sort of familiar things, but this is a more general wave operator. You can show that it's consistent with this gauge invariance, firstly. That's what determines all the relative coefficients, just like in the linearized Einstein theory. So there are, so there's a unique two-derivative wave operator you can write down corresponding to the higher spin field with this gauge invariance. And you can write an action as well from which this follows. This was a linear equation, a linear wave equation. The action is quadratic. It involves this combination, this curly F, which is some kind of analog of the linearized Riemann tensor, a Ricci tensor, and this is the analog of the linearized Einstein tensor times phi. So it's a wave operator. So it's a quadratic action, quadratic in the field phi, and two derivatives acting on phi. And it's easy to check that varying with respect to phi gives you this wave equation. So the challenge, so this is the easy part. So the challenge is to generalize this action and the equations of motion, either the action, which, as I said, has not been done yet, but equations of motion have been done. The challenging thing is to find the equations of motion which generalize to the interacting theory, which promote, firstly, this gauge invariance to a sort of a non-abelian gauge invariance, a diffeomorphism type of gauge invariance. And that's what took Vaselia more than a decade, and you'll see why. So the way in which Vaselia arrived at his equations of motion is to go through a series of sort of recasting or reformulating this simple Fronsdal theory, and then finally finding a form in which you could realize the nonlinear action. And this series of reformulations we will go through at least in schematic steps, so that at least you will have an idea of how this is reformulated. First, we will reformulate the Fronsdal theory in successive ways, and then I'll just mention at the end how it sort of all put together. So any questions about that, about things so far? About the linear Fronsdal theory? By the way, I should mention this is the theory with, it's obvious that it's the theory for the massless gauge fields. You can write down similar actions for massive higher spin fields as well, but that's not a topic I will go into in this set of talks. And also people have generalized to various extent to higher spin fields, which are not completely symmetric tensors, but have all kinds of mixed symmetries. Okay, so the first thing we'll do is to recast this Fronsdal or this linearized theory in a frame-like formulation, and just like we do in general relativity, where we can recast the Einstein action or the linearized action in terms of field binds and connection fields. Alpha will denote one of these coordinate space indices, and A, B Latin indices will denote the tangent space indices. So in general, you have E and omega, which are sort of one forms in space-time, and have, so here A is, of course, tangent space index, which goes from 1 to D, and here this is antisymmetric in A and B. So that's this frame-like formulation is equivalent to the Einstein theory. Here we will recast. For the higher spin fields, the generalization is to go firstly to a set of fields which have S-1 tangent space index and 1 coordinate space index, and for the connection, we'll look at something which has 2 sets of indices. One set which I'll denote by A, which has S-1 index, and then another index B, which is antisymmetric with respect to any one of these indices. So a language that will be useful is that of the Young tableau. So basically, the E will be something which, as far as its tangent space indice is concerned, will be a symmetric tensor of rank S-1. This is the E fields. And the omega fields are basically so 2-row Young tableaus with S-1 indices which are all symmetric, and then there's one index which is antisymmetric, like we have in the Young tableau. So so I claim this that you can reformulate the Fronsdal theory. Well, you have to. It will turn out that this is not enough, but we start by a sort of generalizing in this way, and As we know from the case of ordinary Einstein theory, when you go to this Fierbein type formulation, you get additional gauge invariance because of the freedom of choosing local Lorentz rotations, of doing local Lorentz rotations on your fields E alpha A. So you have not just the diffeomorphism invariance, linearized diffeomorphism invariance, which is like this, about flat space for simplicity, but you also have local Lorentz, the analog of local Lorentz rotations. In this case, it will be something like this, which will involve, so for s equal to 2, you can see that these are the usual local Lorentz rotations, which rotate E with some Lorentz matrix lambda AB, and this E bar is the background around, when you're doing a linearized theory, this is the background around which you're expanding. So to the linearized theory, this is the local Lorentz rotation, which acts on the connection fields like a usual covariant derivative or ordinary derivative. So once you go to this kind of a formulation, you have an enlarged gauge invariance, it turns out that because of this enlarged gauge invariance, you have to add a whole set of extra fields, which are now, in the case of s greater than 2, you have to add a whole set of fields, now involving sort of T boxes in the second row. So that's why you have this omega alpha has s minus 1 indices in the first row and T indices in the second row where T is less than s minus 1. So these things have the same symmetry as this Young tableau. So I'll just stop in a minute or two. So these are 2-row Young tableau, and moreover, we'll take them to be traceless in either, if you contract any pair A indices or B indices, that will reflect this double tracelessness condition. And you can define generalized curvature tensors, which are, again, linearized tensors, which are essentially d omega plus the background E wedge omega, just like we do for, so in the Einstein theory, we have RAB is equal to d omega AB plus E wedge omega. So this is the way in which you define. So for a linearized theory, we expand around the background, and more generally, this will be a Lorentz covariant derivative if you expand around AdS. So you have linearized theories, linearized curvature tensors, which are invariant under a more general Lorentz rotation, which is the generalization of these Lorentz rotations. So the structure is essentially, so I've used a notation over here, which is that A s minus 1 means that there are s minus 1 A indices, and B T means there are T B indices. So it's B1 to BT. So rather than carry around all those indices, I've just followed the Vaselia notation of abbreviating things by the number of indices. And so this is a tensor. This tensor is invariant under this more general local Lorentz rotation, which is, there's a epsilon tensor. I mean, there's a epsilon, which is a gauge parameter, which carries, again, the same symmetries as this Young tableau. So there are, in fact, now many of these gauge parameters corresponding to the, not just the original diffeomorphism invariance, but the generalized Lorentz rotations. So you get a whole family of additional gauge invariances which leave this curvature tensor invariant. And one can show that the equations of motion of the Fronsdal theory are equivalent to setting this curvature equal to 0. This is the analog of the torsion-free condition. So remember, in the frame-like formulation, you get one torsion-free condition which determines omega in terms of E, and then there's another equation which is the Einstein equation which determines E once you've expressed omega in terms of E. So this is the generalization to the more general Fronsdal theory. You have for t less than s minus 1 this whole family of linearized curvature tensors. You set to 0. These are sort of generalized torsion conditions. And then for the maximal one, namely for the Young tableau with s minus 1 rows, that the curvature tensor associated with that is not 0, but instead it's proportional to the wild tensor. And this is equivalent to rewriting, I mean, for the case s equal to 2, this is like saying that you set RAB equal to the wild tensor. So you know that the wild tensor, when the Riemann tensor is equal to the wild tensor, that implies that the Ricci tensor is 0 in flat space. So one equivalent way of rewriting Einstein's equations is to say the Riemann tensor is equal to the wild tensor. And this is just a reformulation of that in the frame language. And this is a generalization of that to this more general case. So let me stop here for a 5-minute break, and then we resume.
Okay. Perhaps also we can invite some questions briefly.
Yeah, this part, I can go over some of this in the tutorial, maybe in more leisure, but I hope you got the sort of general idea.
At least one question.
Sorry, I have, hello?
Yeah.
Just have a naive question. You wrote down the evolution of higher spin fields, for instance, in AdS and in the S space in the last transparencies now. So you have the propagation of higher spin field in a given background, right? So my question is, what about the propagation of higher spin fields in more generic, conformally flat backgrounds? Is it something which has some obstructions or some problems?
Conformally flat. So we'll see that the nonlinear equations require a cosmological constant, at least something which. So you can have, of course, these equations in, say, asymptotically AdS or asymptotically de Sitter spacetimes, but there you need a parameter which has the dimensions of a cosmological constant. So.
So the question is, you said that, you know, if I go to flat space, right? So if I put to 0 the cosmological constant, so to speak, I have problems, right? So flat space somehow is a particular space which is a particularly conformally flat space, right? But if I now take more general conformally flat space-times where I have, as you say, something with the dimensions of a cosmological constant, but something which has non-constant curvature, for instance, right? Are there some pathologies there? Which
No. I mean, so as I said, an asymptotically AdS, so you could do it in an AdS Schwarzschild spacetime, which is not even conformally flat. But so as long as you have a cosmological constant, you can do it in more general class of spacetimes. They need not even be conformally flat. It's just, it's just the presence of lambda that you need.
Okay, then let's take a quick 5-minute break.